This video is on the percent ionization of a weak acid. This kind of goes by several names. You'll sometimes hear it called percent dissociation, or maybe the degree of ionization or degree of dissociation. And even though this is going to be an example where we calculate that for a weak acid, you could do something kind of similar, analogous, for a weak base. So let's think a little bit about what we mean by percent ionization. Alright, so first we're going to start off with a weak acid. So I'm going to represent that by this formula HA. So one thing we know about an acid is a proton donor. So it has to have a proton. There it is. And then A right here simply represents the rest of the molecule. So I once had a student come up to me on an exam and say, "Hey, I can't find A on the periodic table." Okay, so don't be that student. A represents the rest of the molecule. So we know it's an acid. It has to have a proton that we can take off. There it is, and A just represents the rest of the molecule. So since this is a weak acid, it's possible that it could donate that proton to water. Now, oftentimes we will write this as plus water so we can show that water is acting as the Bronsted-Lowry base to accept that proton. But in this case, we're going to just assume that that H gets donated to water, and we're just going to represent that as a free-floating H+. So we know in reality that you can't have a bare proton floating around in an aqueous solution. It's going to associate itself with some water molecules. Sometimes we represent that as hydronium, H3O+, but it might even be more complicated than that. There might be several water molecules that make a cluster around that guy. So anyway, we take the H off as H+, right? So this is why we call it ionization, because we've made an ion. So if you take an H+ off, what's left? Well, the rest of the acid. So we call that A. And since we've taken something with a plus charge off, A has to have a minus charge. Remember, in a balanced chemical equation, not only do you have to have the same number of atoms of each type, but you have to have the same total charge on both sides of your reaction arrow. Okay, so this is what's going on. We're ionizing. We're forming H+ and A-. So how much does it do that? That's really the question that we're asking here. So if you have 100 molecules, do 50 of them dissociate? Does one of them? So here's my example. Imagine that we've got in our beaker of water these 5 HA molecules. Now they're going to dissociate. And so the question is, are they going to dissociate a little bit? So maybe only one of them breaks apart. Let's imagine it's this first one. And is broken apart into H+ and A-. And the rest of the molecules simply stick together as HA molecules in your solution. So this might be an example of what happens if it only ionizes a little bit. What if it ionizes a lot? Suppose that most of these molecules, let's say 4 of them, break apart. What would the picture look like? Well, it might look like this. So now you see we've had 4 of our 5 molecules dissociate, and one of them has stayed together. So which one of these is it going to be? Well, that all depends on the nature of the acid and how good of a proton donor it is, and that's governed by this thing that we call the acid dissociation constant, Ka. So the bigger the equilibrium constant for this reaction, the more it's going to favor dissociation. And so we can write that equilibrium constant expression as products over reactants. So this is going to be H+ concentration times the A- concentration raised to the first power divided by the HA concentration. And these are all going to be concentrations when the system actually comes to equilibrium. So now let's think about this percent ionization. So we want to know what percentage of these molecules in this beaker right here have dissociated. So is it the first case or is it the second case? So let's imagine how we might calculate that percentage in each of these 2 beakers that I've drawn here. So remember what a percentage is. It's a ratio of a part to a whole. So we need to figure out what the part is and what the whole is. So we're trying to figure out the percentage of molecules that ionize. So what we need to know is how many molecules did ionize, that would be the part, and divide that by the whole. That would be the total number of molecules that we started out with, over here in this first beaker on the left-hand side. So in this first picture up here, on my top picture, how many molecules dissociated? Well, we see that right here, just one of them did. We know it's just one because we just got one H+. So every time, according to this reaction, HA dissociates, it makes one H plus ion. So I'm just going to calculate the percent ionization, in this case, by calculating the number that dissociated, and that's just going to be 1. So 1 has dissociated, divided by the number that I started out with. Over here I had 1, 2, 3, 4, 5, so that's going to be 5. So 1 out of every 5 molecules has ionized. And to make this a percentage, we multiply by 100, and that works out to be 20%. So we have 20% ionization in this top beaker. In the bottom beaker, what would it be? Percent ionization. I'm going to just abbreviate that here. Well, it looks like we have 4 protons. 1, 2, 3, 4. So that would be 4 molecules have dissociated out of how many that we started with? 5. So 4/5 of them have dissociated. And we convert that into a percentage, and that's going to be 80%. So we have 80% ionization in this second beaker. So let's generalize this little formula where we've done counting for a real situation where we can't count molecules, but maybe we can count them in terms of how many moles we have dissolved in a given liter. So we're going to write down this general definition for percent ionization. So percent ionization, again, it's a part to a whole. So we want to know the fraction that's dissociated. So in our example, we counted the number of H+. So what would you do in a solution? Well, you would need to know the equilibrium concentration of the H+, the number of moles of H pluses that we have floating around in a given liter of solution. Okay, so and that's going to be at equilibrium. So that would be the part. So just like we counted the H pluses up here, now we have counted the number of moles in a given liter of H+ that we have when we get to equilibrium. So we need to divide that by the whole. And what is the whole? Well, the whole is the HA concentration that we started out with initially. So I'll abbreviate that initially. Sometimes this term right down here, this HA initial, is called the formal concentration. And it's the concentration that you might see written on a bottle of an acid. So if you see 0.1 molar acetic acid, then that's not the actual concentration of acetic acid molecules in that solution. What do you mean it's not the concentration? Well, remember, acetic acid is an acid, it's a weak acid, so some of those molecules are actually going to break up according to our reaction up here. So some of those molecules will break up. So you actually don't have a full 0.1 moles of HA in a liter. You're going to have less than that because some of those molecules will have broken up to give you H+ and A-. So we call that the formal concentration, or just the initial concentration. And then we want to multiply this by 100 to convert that into a percentage. So this is one way of calculating then the percent ionization. So this top number again is telling us how many, or what's the concentration of the stuff that is broken up. And this numerator is telling me, well, how much stuff did you have at the beginning before anything broke up? All right, so let's do a calculation of the percent ionization. So let's do an example problem. In this example problem, we're going to imagine that we're starting off with 0.1 molar nitrous acid, HNO2. So that's nitrous acid. At 25 degrees Celsius, nitrous acid has an acid dissociation constant of 4.2 times 10 to the negative fourth. And we want to know, well, what is the percent ionization? So what is the percent ionization of this weak acid? So if you have a 0.1 molar solution, how many of those nitrous acid molecules will actually break apart? 90%, 50%, 2%, 0.01%? We don't know. We're going to figure that out. So the way to work this problem is approach it as an equilibrium problem. So looking back at our formula, what are we going to need to know? Well, the one thing that we're going to need to know right off the bat is the equilibrium concentration of H+. So we're going to have to calculate that. We also need to know the formal concentration, the initial concentration of HA. And we're actually given that because this is a 0.1 molar solution. All right, so let's think about how we're going to calculate the equilibrium concentration of H+. Well, it's an equilibrium problem. So let's write out our reaction. HNO2. It's going to donate a proton, so we get H+. And our A- now would be NO2-, that's nitrite. So this is the beginning of an ice table. So there's our reaction, change, equilibrium. So initially, what's our HNO2 concentration? 0.1 molar. How much H+ do we have before anything's dissociated? Well, 0 moles per liter, and the same thing for nitrite, 0 moles per liter. So there's going to be some change. So some of this is going to dissociate, so it's going to go away. So we put a minus sign. How much? We don't know. So we're just going to call that x. Let x stand for that unknown amount. So if we lose if we lose x moles per liter of HNO2, we will gain, so plus sign, x moles per liter of H plus and x moles per liter of NO2. Remember that the coefficient that we put in front of the x is the same as the coefficient that goes in front of our balanced stoichiometry. And in this case, it is 1. All right, so we add down the column to figure out the equilibrium concentration. So 0.1 minus x, 0 plus x is x, and 0 plus x is x. There we go. So now what we're going to do is substitute these into the Ka expression. So remember, Ka is products over reactants raised to the power of their stoichiometric coefficient. So H plus to the first power, NO2 minus to the first power, divided by HNO2. And these are all equilibrium concentrations. So I can't plug 0.1 in for this denominator here because that may not be the equilibrium concentration. But what I can do is substitute into this expression what I know each of these terms to be. So Ka, I know what that is. It is 4.2 times 10 to the minus fourth. That's a value that you would have to look up, and it is a property of nitrous acid. So it's something that we can measure and then put in a table. And remember, that is at a temperature of 25 degrees Celsius. At a different temperature, nitrous acid may have a different Ka. Okay, so now we need, according to this equation up here, our acid dissociation equation, we need the H plus concentration. What is it? Well, here's H plus. Here's what it is at equilibrium, so it's X. So then we need the nitrite concentration. So here's nitrite, this column. What is its equilibrium concentration? X, so that's X. Then we divide that by the equilibrium concentration of HNO2. What is the equilibrium concentration of HNO2? There's our column. Here's our equilibrium row. So 0.1 minus X. So this is one equation in one unknown. We could rewrite this x times x as x squared over 0.1 minus x. Now some of you may remember this trick that we sometimes use that's called the small x approximation. Now looking at this equilibrium constant, it's small, 10 to the power minus 4. So we don't expect that very much of this HNO2 is going to dissociate. So we can sometimes use this little rule to help us figure that out. It's called the rule of 100. So we take the concentration that we're subtracting x from. In this case, it's going to be 0.1. And we divide that by the equilibrium constant. In this case, 4.2 times 10 to the negative fourth. And we do that calculation, and that works out for this case to be 238. Now, rule of 100 says that if this ratio is 100 or greater, then it's probably a good bet that you can safely make that small x approximation. So that's what we're going to do. So down here in the denominator, 0.1 minus some number that's really small, that's going to be essentially 0.1. So we take x squared, 0.1 minus x when x is really small is going to be 0.1. So this is the small x approximation. So that makes the algebra fairly easy to solve. We're going to multiply both sides of this equation by 0.1 to get this result, and then we're going to multiply 0.1 through the parentheses to get that equaling x squared. Now we need to get rid of this x squared to solve just for x, so we're going to take the square root of both sides of this equation, and when we're all done we find out that x is equal to 0.0065. Now, since our acid dissociation constant only has two significant figures, we will report x to only two significant figures. So what is x? Well, remember x is up here in this ICE table, so x is the same as the H plus concentration. It also turns out to be the same as the nitrite concentration right here. But what were we looking for? Remember, we're trying to calculate the percent ionization. So we need to know what is the equilibrium H plus concentration. Well, we've just found that. So now we are ready to find the percent ionization. So we use our percent ionization equation, which is the H plus equilibrium concentration, divided by the formal concentration of HNO2. And we multiply it by 100 to make that a percentage. So what's our equilibrium H plus concentration? We just figured it out. It's 0.0065 molar. What was our initial nitrous acid concentration? 0.1 molar. We multiply that by 100. And that result works out to be 6.5 percent to two significant figures. So that tells you if you have a beaker that is full of 1,000 of these nitrous acid molecules, only 65 of them are actually going to break apart into their ions. The rest of them are going to stay together. So this is a molecule that is only weakly ionized in solution. So by percent ionization, we can actually get a count on what fraction of the molecules, what percentage of those molecules actually break apart. We've done this with a weak acid, but you could do the same thing using a Kb value for a weak base, and you could come up with how much a weak base dissociates. So for example, ammonia reacts with water, and the base dissociation reaction would be the formation of NH4 plus and hydroxide, OH minus. And for this, there might be a particular Kb value that you could look up. So in this case, at 25 degrees, it's 1.8 times 10 to the minus fifth. And using that value, we could figure out what the equilibrium concentration of hydroxide is, and then to calculate the percent ionization, we would come up with an analogous formula where we count the number of molecules that dissociated. Well, when an ammonia dissociates, what do you get? You get an ammonium or a hydroxide. So we could use either of those concentrations in our formula. I'll choose the equilibrium hydroxide ion concentration for the base, and then we would need to divide by the formal concentration of ammonia, the initial concentration. And that's how we might figure out the percent ionization if we happen to have a weak base instead of a weak acid.